Okay, so this is a redo of the class of April the 13th. The reason why I'm re-recording it is because when I originally did the class, the wireless kept going in and out, so you can't even hear what I'm saying, and I kept having to redo, and then the second half of the class didn't get recorded because when I re-entered, it did not record anything after I re-entered about 30 minutes into the class. So I'm recording from my parents' house in Columbia, South Carolina, and then I'll post it for one of your colleagues who's not feeling well. Okay, so this is a redo of the class of April the 13th. So what we did on April the 13th is we started chapter 16, thermodynamics. So we had actually done a chapter on thermodynamics earlier in General Chemistry 1. This is the second half of that. So we're just going to introduce some new topics that we did not discuss in Thermo 1. Okay, so the first topic that we're going to talk about is the idea of spontaneity. So you can have a reaction that's spontaneous in one direction, and often it's non-spontaneous in the opposite direction. So for instance, the reaction of hydrogen and oxygen is explosively spontaneous. You put a little spark to it, it explodes and gives you water. The opposite reaction, water does not spontaneously give you hydrogen and oxygen. And we know this is true because if water just naturally dissociated to hydrogen and oxygen, we'd have little explosions every time there was water anywhere in the room. And that's not true. However, you can get a non-spontaneous reaction to go by adding energy. If you input energy, you can always get a non-spontaneous reaction to go forward. Oops. So what is entropy? So entropy is a measure of disorder in the system. So if you have two gases, two bulbs in a glass container, and one side has gas, there's a little valve, and then the other side has a vacuum. What'll happen is if you open the valve, the gas from this side will flow to the other side, and then you'll have a dispersal of the gases. So you'll end up with the same amount of gas on both sides of the valve. Now, what is the process of the gas going from this side to that side? Are you changing energy? Is anything getting hotter? No. So you're not really changing energy. What you are doing is you're changing disorder. So this is a very ordered system because you got all the gases in one bulb. When you let it out and then the gases all disperse, you've got less order. It's more disordered. So this is an increase in disorder, but no change in heat or any other energy. So here we have another idea of disorder. So you got two objects, one is hot and one is cold. So X is hot and Y is cold. If you put the two objects in contact, the heat will disperse from X to Y, and then you'll eventually end up where X and Y have the same amount of heat. But if you look at it from the outside, we're not changing the energy of the combined XY because it's just moved to a different place. What we are changing is the amount of disorder we have. In this case, it is very ordered, hot and cold. In this case, it's all mixed in, so it's got more disorder. So spontaneous processes usually increase disorder. So a spontaneous process is if you're trying to go down a hill in energy or down a hill on an actual literal hill, you are going down energy, and downhill in energy is always a spontaneous process. So entropy is defined as the amount of randomness in a system. So something that's a solid versus like water, a solid form of water, the liquid form of water versus the gaseous form of water. As you go from solid to gas, you're actually increasing the amount of disorder because in a solid, the molecules are nicely locked in a specific way. They're not moving around at all. You add a little bit of energy to it, a little heat, And now the molecules are moving around. There's more randomness because the molecules are moving around any old way they want. And when you heat it to the point that you get a gas, you have even more disorder because the molecules are now randomly moving around any old way they want, much more than they were in the solid. So this is all an increase in the amount of entropy or randomness. So here's a solid, nice little pack of solid crystalline things. Liquid, they're all distributed. There's no specific way that the molecules are set in a crystal structure. They're sort of randomly situated. In a gas, they're just floating around any old way. So in going from solid to liquid to gas, you are increasing the amount of randomness or the amount of disorder in the system. Entropy, the disorder, is another state function, meaning it doesn't matter how you get to the state. All you're worried about is the delta S of the system. The difference in entropy of the system is equal to the final entropy minus initial entropy. It doesn't matter how you get from final entropy to initial entropy. You can take a circuitous path, or you can just go straight from one to the other. Doesn't matter. It's just a state function. So all that matters is the final state and the initial state. This shows the percentage or the fraction of molecules at a given temperature, and this shows kinetic energy. So if you increase the temperature, so this is temperature 1, this is temperature 2, where temperature 2 is higher than temperature 1. So what happens if you increase the temperature is, at the initial temperature, you have sort of a bell curve where you have the very low energy, very low kinetic energy molecules. You have a very small fraction of very high kinetic energy molecules. And then you have a section where you sort of have the majority of the molecules having this kinetic energy at that given temperature. Now, when you increase the temperature, you increase the average kinetic energy of the molecules. You increase the initial, the smallest fraction at the lowest kinetic energy, and the highest kinetic energy, you change that. But you also change the average kinetic energy. But not only do you change the average kinetic energy, look how this is a nice tight curve, and this is now a spread out curve. So when you increase temperature, you also increase the amount of randomness because you have a greater spread of the kinetic energy in the molecules. The molecules are not all tightly packed into this average kinetic energy. They're all sort of spread out. So this shows entropy versus temperature, and then you have the solid, liquid to gas. As you start with a solid, as you increase the temperature, the amount of randomness increases. And then there's a sudden jump as you go from solid to liquid. And then as it is a liquid and you keep heating it, it keeps the entropy keeps rising. And there's a big jump as you go to the other state. So states of matter have a lot of an effect on the amount of randomness you have in a system. So solids have the lowest entropy, gases have the highest entropy. So we already discussed this when we were discussing Thermo 1, but what is a system? It's the part of the universe that you're specifically looking at. So for instance, the reaction inside a coffee cup, perhaps. The coffee cup content and the rest of the universe outside being the surroundings. For chemists, we don't usually think of the surroundings as being very far out, to the outer reaches of the universe. Usually the surrounding is usually fairly focused right around the system that you're looking at. So you can have entropy changes in the system and the surroundings. So the entropy of the surrounding is directly proportional to the change in the enthalpy of the system. So the entropy of the surroundings is inversely proportional to temperature, and is directly proportional to the enthalpy of the system. The entropy of the universe is equal to the entropy of the system plus the entropy of the surroundings. This is actually a statement of the second law of thermodynamics, which says that there is a spontaneous increase in the entropy of the universe. And but the systems and the surroundings can be added up to get the entropy of the universe. But for a spontaneous process, the entropy of the universe always has to be positive. So for a process to be spontaneous, entropy must increase for the entire universe. The entropy for a system and surroundings, the entropy of the system might actually decrease, but overall, the entropy of the universe must increase. So second law of thermodynamics, there is an increase in the entropy of the universe in anything that is a spontaneous change. So we have the entropy of the universe is equal to the entropy of the system plus the entropy of the surroundings. The entropy of the universe is greater than 0 for all spontaneous processes. Change in entropy is less than 0 for all non-spontaneous processes. The entropy of the universe is equal to 0 for a system at equilibrium. The third law of thermodynamics says that the entropy of a pure, perfect crystalline substance at 0 Kelvin is 0. 0 Kelvin is almost impossible to achieve. But when you achieve 0 Kelvin, you have 0 entropy. There is no lower temperature than 0 Kelvin. And when you achieve 0 Kelvin, that means that all molecular movement has completely stopped. There's no movement at all. The entropy is 0 at the point when there's no molecular movement at all. Standard entropies, S0, is defined for 1 mole of a substance at 1 atmosphere and 25 degrees Celsius. So entropy, standard entropy, if you have a aqueous solution, it has to, the standard entropy, the little 0 there must be at 1 molar. Standard entropies, unlike enthalpy and free energy, is almost never 0, even for an element in its most stable form at standard conditions, because you've got 25 degrees Celsius, which is not Kelvin. You can also take differences between standard enthalpies to entropies to generate the standard entropy change, delta S0. So here's the table of entropies for various molecules. Now you note that things like hydrogen, H2 gas, when you're looking at enthalpies, those for the element in its most stable form is 0. Entropy, it's not 0 because it's at 25 degrees Celsius. It's not at 0 Kelvin. At 0 Kelvin, it would be 0, but not at 25 degrees Celsius, the standard entropy condition. Elements like carbon, also not 0. But here's a table of entropies, and you know what you're going to do with a table of entropies. You're going to develop an equation for a reaction based on your little table there. So here's an equation for how you would get the enthalpy of a reaction, the entropy of an entropy change of a reaction, the free energy change for a reaction. And the equation is pretty much the same for all three. We're already familiar with the enthalpy equation. when you do the entropy equation, all you do is same thing. You just put in, instead of putting delta H F of 0, you put in S of 0. For the free energy version, you write down delta G F 0. And then, but for a reaction, it's always the number of moles of each of the reagents in the product minus the number of moles of all the reactants. So you add up all the products, you add up all the reactants and subtract one from the other. And you have to take into account the number of moles in your equation that you're trying to calculate the enthalpy of formation, the enthalpy at standard conditions, the entropy at standard condition, or free energy at standard conditions. You're doing it for a particular reaction, and you have to take into account the number of moles. You add up all the products, you add up all the reactants, and subtract one from the other. So if you have a generalized equation for a reaction, number of moles M of molecule A, number of moles N of molecule B, going to give you X moles of molecule C and Y moles of molecule D, then the equation for the free energy would be X moles of the heat of the Gibbs free energy of formation of molecule C plus number of moles of molecule D times the Gibbs free energy of formation for molecule D, and then that's all of your products, minus, and then you take all of your reactants and add those together and subtract it from the products. So the number of moles of molecule A times the Gibbs free energy for molecule A plus the number of moles of molecule B times the Gibbs free energy for molecule B. You add those two together, and then you subtract it from all of the products that you also added together. So this is the Gibbs free energy is equal to number of moles Gibbs free energy of formation of products minus the number of moles of Gibbs free energy of reactants. And you got the little summation signal sign there because you're saying all the products added together, all the reactants added together. So there's the equation. So Gibbs free energy is something that you can use to predict spontaneity. And it has a enthalpy term, the heat term, and it has the entropy term, the disorder term. And the equation is Gibbs free energy is equal to enthalpy minus T delta S. So the spontaneity term, Gibbs free energy, is equal to the enthalpy minus the temperature times the amount of disorder you have. So the heat and disorder. So spontaneous processes are favored by a decrease in enthalpy. So if you have a negative delta H, the reaction is more likely to be spontaneous because that G, if it's negative, it's a spontaneous process. So if H is negative, it's more likely to be spontaneous. It's favored by an increase in entropy, positive delta S. So reactions spontaneously become more disordered. Reactions spontaneously release heat. Non-spontaneous processes are favored by a positive delta S and a negative delta S. So it becomes less disordered, and the reaction actually needs to have heat added to it in order to make the reaction go. So that is not a spontaneous process. So Gibbs free energy, the spontaneous term, enthalpy of the reaction, negative delta S is spontaneous, reaction releases heat. Here's my temperature term, here's my entropy term. Delta S is spontaneous. This is when it becomes more disordered. And at higher temperature, the entropy has more of an effect. At lower temperature, the enthalpy has more of an effect. So spontaneous reaction goes forward. Delta G is negative. It's more likely if delta H is negative. It's not always going to be spontaneous because it also depends on the entropy term. But in general, if delta H is negative, it's more likely to be spontaneous. If delta S is positive, it's more likely to be spontaneous. So if both delta H is negative and delta S is positive, then delta G will be negative. So the process will be spontaneous if your reaction releases heat when the reaction occurs, and when there's more disorder when the reaction occurs, then the reaction will be spontaneous. Okay, so delta G less than 0, process is spontaneous, reaction goes forward. Delta G is equal to 0, it's at equilibrium. Delta G greater than 0, it's non-spontaneous, reaction goes back to the reactant. At high temperature, entropy decides. At low temperature, enthalpy decides. So based on what we just said, you can go ahead and complete the table. So if enthalpy is positive, that's not a spontaneous thing. If delta G is positive, that would be more spontaneous. And if you have a large temperature, then the entropy will sort of take over. So then it probably would be spontaneous. So here's how this would translate. So if enthalpy is positive and entropy is also positive, but T is very large, it would be spontaneous because you got a negative term there, negative T delta S. So T delta S, negative T delta S is large. So then delta G is also going to be negative. If delta H is negative, that means that it's the reaction is releasing heat. And delta S is positive, that means the reaction is becoming more disordered, and temperature is small. Then the thing that sort of swamps it out is the enthalpy. This says that it's going to be it's going to release heat during the course of the reaction. That is a spontaneous process. It's also negative. I wouldn't worry so much about this homework problem. I did give that as a homework problem. Sort of makes you think about how this works, but I wouldn't worry too much about this homework problem. Okay, here's my second homework problem. So this question says, if the enthalpy is 42 kilojoules and entropy is 111 joules per Kelvin at 400 Kelvin, what is delta G? And B, is the reaction spontaneous? So we can go ahead and work this problem. I think I actually gave the answer in the next slide. We can go ahead and work on this. So the way you would do this is you would say, oh, let me plug in everything. Now you have to watch out for the units. Why do you have to watch out for the units? Because enthalpy is almost always given in kilojoules and entropy is almost always given in joules. Why is that? It's just sort of a convenient term because the size of the numbers that you have, but you have to watch out for the units. So delta G, so here's the equation, delta G is equal to, oh, I covered up all the numbers there. So let's see, delta G is delta H minus T delta S, and we said delta H is 42 kilojoules. We said delta S is negative 111 joules per Kelvin. And we said the temperature is 400 Kelvin. Okay. So then all we have to do is just plug everything into the equation. This is as easy as the gas law problem. All you do is just plug in all the numbers into the equation. You just have to watch out for the units. So the temperature is in Kelvin, so we're going to say 400 Kelvin. Delta S is in joules per Kelvin, negative 111 joule per Kelvin. Now, a hint I have about how you should generally try to do an equation on a test. The way I grade your tests, I give you partial credit for setting up the equation correctly. And then if you make mistakes in the algebra or math going from the plugged in equation to the final answer, I don't take off that many points. Sometimes I only take off, even if it's like a 10-point question, I may only take off a point or two. For a algebra math problem, I can tell you set everything up correctly. This is all there. And then going from here to the final answer, you did something wrong. I look at your algebra. I'm not sure exactly what mistake you made, but you ended up with something ridiculous for your final answer. And then I'll say on there, algebra math -1 or some -1 or 2 or something like that. So it's in your best interest to go ahead and always set up the equation with everything plugged in. Now, if you were trying to look for the easiest way to do a reaction, I would not plug in numbers, because if you just leave it like this, and then you worked through the equation, did the algebra with just the symbol, it's usually easier. But just to make sure that you get the points for knowing what goes into what part of the equation, I would just go ahead and plug it in. Now you have to watch out for the kilojoules to joules, because this is kilojoules. So let's go ahead and change everything to joules. So I'm going to say 42 kilojoules. There are in 1 kilojoule 1,000 joules. So I made that change, and then I'm going to say 400 Kelvin negative 111 joule per Kelvin. So then you notice what cancels out. First the kilojoules cancels, so it ends up being joules. Kelvin cancels, Kelvin cancels. And then I end up adding 1 joule to another joule. And then let me show you what the answer is, which is on the next slide over here. So that's what we get. And we notice that delta G is a positive number. So for the reaction to be spontaneous, delta G actually needs to be negative. So is the reaction spontaneous? No, it is not. Not spontaneous. Okay, so then we have this K is not Kelvin. This K is the equilibrium constant K. Remember where you have K equilibrium constant is equal to the products on top divided by the reactants on the bottom, things in brackets with the coefficients going as the power of the reagent in the inside the brackets. The reactants in brackets raised to the power. Remember that equilibrium constant expression? So we're going back to that K. So that K is where you got A moles of molecule B, B moles of molecule B, going to give you C moles, molecule C, plus D moles of molecule D. And then you get K, the equilibrium constant, is equal to C raised to the Cth power, D raised to the Dth power, A raised to the 8th power, and B raised to the Bth power. Remember that, this equilibrium constant? So this K here, this K is this K. So this K right here is this K. So that's the equilibrium constant. It's not Kelvin, it's the equilibrium constant. So the relationship, and there's a derivation in your book if you want to look at it, but the derivation results in this equation. So when you have equilibrium, the free energy is equal to 0, and if free energy is equal to 0, Q, the number for equilibrium for things plugged in, would equal K. So then you end up with the Gibbs free energy is equal to negative RT natural log of K, the equilibrium constant. So that means you can actually relate the thermodynamic Gibbs free energy term to the equilibrium constant. So here's homework 16.3, and homework 16.3 is where you're supposed to calculate delta G, delta H, and delta S from the given chart. So you're given this chart and you're given this equation. This is actually one of the examples in your textbook. Okay, so you got the equation that starts with the reactant mercury oxide. you're generating mercury liquid and oxygen gas. And here's the balanced chemical equation with the coefficients there. The mercury oxide, the Gibbs free energy is negative 58.43. Why is this zero? Because Gibbs free energy for elements in its most stable form is always zero. Why is this zero? Why are these zero? Because the enthalpy of formation for the element in its most stable form is always zero. So sometimes you'll actually get like a question where people will give you the number for the one that's not zero. Like they'll give you the enthalpy of formation of HGO is negative 90.46. And then they'll ask you, what is the enthalpy of the reaction? And you'll say, well, you didn't give me the enthalpy of formation for mercury liquid. You didn't give me the enthalpy of formation for the oxygen as for oxygen gas. Where am I supposed to find that? Is there a chart that I'm supposed to look this up on? No, it's just the element in its most stable form. It's always zero. Okay, so this is a very simple problem because all these things are zero. But note that the entropy is not zero. See, entropy not zero. Why not? Because entropy at standard conditions is at 25 degrees Celsius, which is not 0 degrees Kelvin. If it was 0 degrees Kelvin, the entropy would be zero, but this is not 0 degrees Kelvin, so it's not equal to zero. So how do you calculate this? So this is where you go, the following equation on the next slide. This is just basically, you're using this equation on this set of data. That's all it is. All right, so let's start out with the Gibbs free energy. So Gibbs free energy at standard conditions is equal to, and let's write down the equation. So summation of N delta GF0 product minus summation number of moles delta GF0 reactant. Okay, so the equation that we have is, let's see if I can move this over so you can actually have, oops, both this and this on the same thing at the same time without having to. Okay, so our equation is we've got product. So the product, so if I rewrite this in this equation in terms of the actual species that we have in our actual reaction, products is number of moles, so N of Hg times delta GF0 of Hg, and this is Hg liquid, and the other product is oxygen plus number of moles of oxygen times delta GF0 of oxygen liquid. Oops. Okay, just trying to click on that. Okay. Minus, and you only have one product. So if you had more than one product, you'd actually have to add them together, but you only have one product. So you have number of moles of H2O times the free energy, gives free energy of formation of HGO, and HGO is a solid, I believe, right? So there's our equation. So there's our equation. So we can go ahead and plug in what we have there. So then you say gives free energy is equal to the number of moles of mercury is 1 mole mercury times the gives free energy of mercury is 0, right? Plus, how many moles of oxygen do we have? We got half mole oxygen times, and what do we have for the value of delta G of free energy for oxygen? 0. Okay, so you add those two together, and then you subtract from that and then you subtract from that, you can't see it. Okay, so you subtract from that the number of moles of the mercury, so the mercury oxide. So the number of moles of mercury oxide is 1 mole of mercury oxide times, and then we've got the number for that here. The number for that is negative 58.43, and the units are kilojoules per mole. And that's all we have for our reactant. So we don't have to write more than, you can just write it in one line. So then it's 0 plus 0 is 0. So then this entire thing becomes delta G is equal to negative or plus 58.43 kilojoules per mole. And then you do something similar for the other. So then you do something similar for the enthalpy as well as for the entropy. And I think I actually have that on the next lecture recording. Okay, so that is the end of the material that we covered on April. This is a redo of the class of April the 13th. So this is it. Okay, all right. So that takes care of the first part of the Thermo 2 chapter. Okay, and I will shortly post it.